complex analysis. This is going to be a new series. What we are going to do is we are going to prove all the main results about holomorphic functions. In the last series, we developed what is known as Cauchy's theory, which resulted in Cauchy's theorems of various kinds. Okay, and Cauchy integral formula, analyticity of holomorphic functions, etc., etc. Okay, so these we will get started. Today what we plan to do is we are going to prove a very basic but very easy result, of course given all our work earlier, the so-called Morera's theorem. Okay, let's get to work. So what does the theorem say? Morera's theorem says, okay, gives a criterion for a continuous function from U to C. Okay, criterion for its holomorphicity when f is holomorphic. Okay, so let us say what the theorem is. Okay, it says that let f from U to C be continuous okay, and I assume that for any triangle delta contained in U, okay, we have integral of f over t is 0 where t is the boundary. Okay, then conclusion, then f is holomorphic. You see that this gives, I am given a continuous function if the integral path integral of f over the boundary of any triangle is 0 where the triangle should be contained in completely in U. That is very important always. Okay, then f is holomorphic. Yeah, and the result, the proof is extremely easy. It's almost deceptively simple. Okay, now let's go back. If by Cauchy-Gursa, okay, and its corollary, Cauchy's theorem, we know that the hypothesis says that it's actually a proposition before that. Okay, sorry, it's not by Cauchy-Gursa. You see, I told you it's a deceptively simple. You see that? I am also deceived. Do you remember we proved a theorem if you use open set, okay, and assume that f is a continuous function U to C, and assume that integral f over t is 0 for all triangle delta contained in U, then f has a primitive. Okay, this is a proposition. Okay, recall this. So by the quoted proposition, okay, f has a primitive g. What is this g? G is a function from U to C, and says that g dash equal to f, right? Therefore that means g is holomorphic, right? But any holomorphic function we have seen, this is because g is, I'm just recalling, analytic and hence infinitely differentiable. Therefore g double dash, namely f dash, exists. That means f is holomorphic. Okay, go through the proof, enjoy. Okay, and used a highly non-trivial result. The simplest result here which used as a proposition. Whenever I have a continuous function and whose path integral over a triangle is 0, whenever the solid triangle is contained in U, then it is a primitive. That's a very easy proposition. Okay, but what we did was, once it has a primitive called the primitive as G, that's holomorphic. Then we are using the fact G is analytic. You see, that's one of the basic fundamental results of Cauchy's theorem, right? It's analytic, and hence it's infinitely differentiable. Therefore G double dash also exists, but G double dash is nothing other than F dash exists. That means F is holomorphic. Do you like this proof? Isn't it amazing? Okay, so the QUD proof is over, right? Now let's just do some stock taking. To okay, so suppose I have an open set and a function C. Okay, what are the ways I can show F is holomorphic? I want to show F is holomorphic. Okay, what are the ways? The first way is from the definition. By definition, check. Okay, F dash exists for all Z in U. Okay, second thing is write F equal to U plus IV, right? And then show F. Okay, U and V satisfy Cauchy-Riemann equation, and the partial derivatives of U and V are continuous. Okay, this is the sufficient condition we have proved. Third thing is, okay, exhibit F as a Cauchy type integral. Okay, of course I forgot a fourth one. This must be the fourth one. The third one, by algebra of holomorphic function, including chain rule, functions composition rule, etc. What does that mean? The function F, okay, is algebraic combinations, okay, use of various algebraic manipulations of holomorphic functions and composite of holomorphic functions. So express this, okay, F was got by means of various operations, algebraic operations or composition operations of holomorphic function. Therefore I can consider as F is holomorphic. Okay, and fourth one is show that F is of the form, okay, some Cauchy type integral G of W by W minus Z wherever for Z in the domain of U, right? Now this is the fifth one is Morera's theorem. Okay, this is one of the most powerful ways. Okay, is a most powerful way of showing if a function is holomorphic. Okay, let us look at some simple example. Okay, so let us look at one example. Suppose F is a, let us say G. Okay, G from U to C is a, or maybe no, G from 0 1 to C continuous, right? Then let's look at F of Z equal to G of T into sine of Tz dt 0 to 1. Okay, now I want to claim this is for every Z now. Notice that for every Z in C, this integral exists. Why? T going to G of T is continuous, T going to Tz followed by sine of that, that's a composite of continuous function, therefore it's a continuous function, product of continuous function and the closed and bounded interval, therefore I know the integral exists. Okay, but since I integrated over T, it's a function of Z only. Okay, then I want to claim F is holomorphic. Okay, now how do I prove that? So one way may be just to, as I said, start from the definition of the derivative and try to find out. Now I can use, okay, Morera's theorem. Let delta be a triangle, t be the boundary, right? Then I only have to show integral over t of f of z dz is 0, right? But this is, okay, integral 0 to 1 g of t sine tz dt, okay, dz, okay. Okay, this is your function f of z dz. Now remember, this is a path integral, right? Now remember, t is compact and 0 1 is compact, therefore this is compact, and the integrand is a function of two variables t and z. Okay, this is a function of two variables t z. Okay, as a function of these two variables is continuous. Therefore I can use Fubini theorem, okay, for compact, okay, sets in advanced in several variable calculus, or if you learn measure theory, then you can use this, right? Therefore this is equal to 0 to 1 and over t, right? And g of t comes out and I have sine tz dz, okay, into dt. But this is 0 because this function is holomorphic. Yeah, Fubini theorem allows us to change the order of integration, so I interchange that. But then notice that gt will be inside, but it is independent of z, therefore it's a constant, I can take it out. Therefore this is just a path integral of this holomorphic function over the triangle t. And remember, the t is the boundary of delta and delta is contained in u, right? Therefore Cauchy's theorem, sorry, Morera's theorem conditions are, sorry, Cauchy's theorem is valid, therefore this is true. Alright, this is actually Cauchy-Gursa. Okay, this is 0 by Cauchy-Gursa. Okay, all you can also say Cauchy because that's more general than Cauchy-Gursa, but what all I needed is Cauchy-Gursa here, because this is, okay, this is a holomorphic function integrating over the boundary of a triangle where the triangle is contained in u. Then Cauchy-Gursa said the integral is 0, right? Okay, so this is one typical use. Slightly more advanced example is, let us look at, let me see, 0 to infinity of e power tz by 1 plus t dt. Okay, let us define f of z to be like this. This is exactly like the similar one. You see that? Now, note this is for which z this makes sense. Okay, okay. When does this make sense? For an analyst, you should be worried about this thing, right? So only for those values of z for which this integral makes sense, I can expect, okay, to show the f is holomorphic. Let me just make sure I share the screen. Yes. Okay. Now notice that t is positive. Therefore, now let us look at. So the only way is I would look at, see, 1 plus t is below, okay, and here, and if you know 0 to infinity, something like 1 by t, there is always a problem, right? But let us look at it. Okay. See, e power tz by 1 plus t, I want to look at this modulus, that is going to be e power tz modulus by 1 plus t, but t is positive, but then this is less than or equal to e power tz, right? Therefore, if I want to look at when the improper integral converges, I have to look at this value. But you may remember e power z is e power x plus iy, therefore mod e power z is e power x. Therefore, this is nothing other than e power tx. Yeah. Now let's go back. So this is going to be dominated in modulus is going to be dominated by e power tx, right? And t is going to vary from 0 to infinity. So if x is positive, okay, this will shoot to infinity, and 1 upon 1 plus t is not going to be of any use. You follow that? Yeah, because towards infinity, if I had to be integrable, it should be something like 1 upon t squared. Okay, higher power of t should be at the denominator. When it is 0 to 1, it should be the other way around, but it's okay. 1 plus t is positive, so I do not worry about. Okay, are you following me? Yeah. So what does this mean? So I should look at only z such that real part of z is less than 0, because in that case this will be e power tx. As t goes to infinity, e power tx will go to 0. So there is some scope of convergence, right? So therefore assume, okay, x equal to real part of z is less than 0. Therefore this one 0 to infinity e power tz by 1 plus t in modulus dt is less than or equal to 0 to infinity e power tx dt. Yeah. So let us put u equal to tx. Therefore du equal to x dt, and when t equal to 0, etc., etc., the thing. So this is going to be 0 to infinity e power u, du is going to be x dt. Yeah, so dt is going to be du by x, 1 by x. Okay, this is 1 by x, and e power u between 0 and infinity, therefore it's minus 1 by x. Okay, so we have shown, therefore f of z makes sense if real part of z is negative. So I'm sorry, I forgot today. Pause, review, proceed. Okay, in fact you should do at 3 places. Okay, one is after the proof of Morera's theorem, Morera, PRP, then identifying holomorphic functions PRP. Now the examples, example 1 PRP and example 2 PRP. Okay, I'm sorry, I don't know why I got carried away, because this is what happens. Okay, I have something I want to finish, so I try to go. This is very bad. Usually I don't do that such things, but anyway, is it okay? Right. Now let us go a theoretical application. Okay, application 2. Oh, I have not proved it. Yeah, yeah. Okay, after that, okay, it makes sense. Okay, now apply Morera theorem and Fubini as earlier. Therefore integral over t f of z dz is going to be integral over t 0 to infinity, okay, e power tz by 1 plus d dt dz. But that, okay, now you see that now I am an improper integral. Therefore the standard Fubini theorem, as you have learned in several variable calculus, which is valid only for compact rectangles or something similar regions, it may not be valid. But if you go through, you know that, okay, the absolute value of this iterated integral, okay, I have shown it converges. Okay, are you following what I am saying? This is going to be something like minus 1 by x. I am integrating this over t. That's a continuous function, right? Therefore the integral over t, integral over 0 to infinity of this dt and dz, okay, exists. This is not equal to, okay. Therefore by Fubini tonally, in case you don't know such things, ignore. This is done in measure theory possibly. Okay, I can interchange this. So this will become 0 to infinity. Okay, Beniternally hypothesis says one of the iterated integral exists, then the other iterated integral exists, and the double integral exists. All three are equal. Okay, those who have seen my lectures on double series, similar thing uh, we proved for a double series sum, and there also I quoted analog of Beniternally. I proved it there though. Okay, anyway, so it is e power tz by 1 plus t dz into dt by this is 0 by Cauchy-Gauss. Okay, so p r p. Okay, now we will go to a theoretical application. Suppose u is are open, and suppose happen to C are holomorphic for each natural number n. Assume that this hypothesis Fn converges uniformly okay, to some function f on compact subsets. On compact subsets of u. Right? What does that mean? You give me k, a compact subset of u, okay, then F1 converges to F uniformly on k. Okay, I do not know whether F1 converges to F uniformly on all of u, only on compact subsets. Understand this? And this is very important. Again, let's make a digression. As I keep saying, this is how one learns mathematics and one tries to relate and understand. Remember, if I define a power series function Cn z power n whose discover convergence b0r, then what did you do? Then let's look at the partial sum ck z power k equal to 0 to n. This converges uniformly to this function f, okay, only on b0 r, 0 less than or less than r, right? So in particular, if you want, I can say r less than s and less than capital R. Therefore, this even the closed ball is contained in this. Okay, this is a closed and closed and bounded set. Therefore, by Henry-Borel theorem, it's compact. So, in the power series case also, what we saw was, okay, the partial sums of a convergent power series converge uniformly to the sum or the function, okay, only on compact subsets of B0 of the disk of convergence. Okay, maybe I will explain this, okay, a little more. Suppose K is a compact subset of B0R, right? Now let's look at, I have an open covering of B0R, namely B0R as R, okay, lies in 0 to capital R. Okay, this is an open covering, right? An open covering, and the union is R is B0R, right? Therefore, since K is compact, okay, there exists some R1 to Rn such that K is contained in union B, okay, 0 Ri, I equal to 1 to n. But remember, if I assume R1 less than R2 less than or equal to Rn, okay, okay, therefore this is nothing other than union is Brn, B0 Rn, right? You follow that? Yeah. Therefore, K is contained in B0 Rn, and remember Rn is strictly less than R. Therefore, F, the partial sum Sn converges uniformly to F on B0 Rn and hence on K. On K also, because K is a subset of this. Yeah. So please understand, because these are the things which are usually never explained. You should understand why for complex analysis uniform convergence on compact sets is more important than uniform convergence on the entire domain. I just want to emphasize this point. You will see for complex analysis, when I deal with holomorphic functions, etc., the most important concepts of convergence for functions is not uniform convergence on the domain where fn's are holomorphic. What is more important is fn's converge uniformly on compact subsets of U. Fn converges to F uniformly on any compact set K of U. It may not converge uniformly on all of U. For example, power series is one such example. Please remember that this is a very important concept. That's why I thought I will just digress, but I actually digress a bit deeper. Okay, please understand that. We will go back. Okay, now let's come back. Now my assumptions Fn are holomorphic and Fn converges to F uniformly on compact sets, subsets of U. Yeah, right. Now first notice that then F is continuous. First conclusion, why F is continuous? Okay, as I said earlier, okay, suppose K is a compact set. Okay, let us look at various Z in U and let us look at B, Z, R, Z. Okay, this collection, so that B, Z, R, Z is contained in U, and this collection as Z varies over U. This is an open cover, right? Yeah, right. You understand? Well, let us make even 2RZ. Okay, are you following? So for each Z in U, choose RZ such that BZ 2RZ is contained in U. Then this collection B, okay, Z RZ as Z varies over U. This is an open curve. Cover of U and hence of K. Therefore, there exist finitely many things so that my okay, maybe when you use 2Z, just allow me. Okay, let us work with this. Therefore, let us assume B Z I 2R. Let me call it only 2RI. Okay, RZI. I will call it as RI. Okay, 1 less than or equal to I less than or equal to N is a finite cover. Right. Now let's look at the closed ball. Yeah, see, this is why I just wanted something. Okay. So let us do 3/2 or something. Okay. So I have an open cover. I have this. Therefore, Fn converges uniformly to F on B Zi Ri. Okay. Or no, let us. It's all right. Let us assume this. Okay, this. I'm sorry. Let me go back. I got my ideas clear. So let us look at this cover. Bz Rz Z varies over S and extract a finite subcover Bzi Ri 1 less than or equal to I less than or equal to N, where Ri is Rzi, etc. Right? Now let us look at Fn. This converges uniformly on to F on any B Zi 3 Ri 3 by 2 Ri. Okay, this closure, and this is contained in B of Zi 2 Ri, and that's contained in U. Okay, this is a compact set. Yeah, you follow that? This is uniform. Now Fn's are holomorphic, therefore they are continuous, and therefore this F is continuous, where on B Zi 3 by 2 Ri for each I, right? Okay, in particular they are all continuous on B Zi Ri for each I. But given any Z in U, right, then Z belong to some B Zi Ri. There is I so that Z belong to this because of finite cover, right? Therefore F is continuous on B Zi Ri, therefore F is continuous on Z, and Z was arbitrary. Sorry. Okay, therefore we have proved the limit function F is continuous on U. If this is the first time you are going through this kind of argument, please go through it. Okay, now we are through. So now I have Fn, okay, holomorphic functions. Fn converges to F uniformly on compact sets. Okay, then F is continuous on U. Then what do I want to show? I want to show F is holomorphic. Okay, now what does Morera's theorem say? To show a continuous function is holomorphic, let delta be any triangle in U, then I have to show integral of f over t is 0. Right? Now let's look at now Fn's converge uniformly to F on t because t is compact. Right? And you have seen when we did path integral, therefore integral Fn over t converge to integral f over t. But Fn's are holomorphic on the open side U, and the solid triangle delta is contained in U, therefore by Cauchy-Gurza this is 0. Right? This is true for all n, therefore this is 0, and hence F is holomorphic. Okay, there is actually a stronger version due to Weierstrass that we will do later as and when necessary. Okay, it not only says under stated assumption, okay, all the nth derivative, kth derivative of Fn also converge uniformly on compact subsets to the kth derivative of F, because F is holomorphic, right? Therefore kth derivative of F will exist. What it says is, okay, just because Fn converges to some function F uniformly on compact sets, we are going to claim F is holomorphic, and also the kth derivative of Fn converges to the kth derivative of F uniformly on every compact set. Okay, that is known as Weierstrass theorem, but that will be a separate video. Okay, right. Now before I go further, I think this is more than enough. Okay, there is one Riemann theorem. Okay, let one more application. Sorry, one more application too. Okay, this is again theoretical application. Suppose F from U to C is continuous and F from U to Z0 to C is holomorphic, that is except at a point, okay, it's holomorphic. Then F is holomorphic on all of U. See, this you can see these are all like bootstrap arguments which I talked about in my summary. Okay, how do I prove that? Okay, to notice that F is continuous, therefore by Morera theorem, you have to show integral of F for T is 0 for all triangle data contained in U, and T is the boundary, right? Okay, now remember F is continuous from U to C and holomorphic except holomorphic on U except at Z0, right? Now do you remember our extended Cauchy-Gursa implied integral of F over T is 0, right? Do you remember that's precisely extended Cauchy-Gursa, right? Therefore what I have proved, F is a continuous function and holomorphic except at one point, it's a holomorphic always. Then I want to show F is holomorphic everywhere, that is F is differential at Z0 also, right? I want to show it's holomorphic on U. Instead of showing F dash at Z0 exists, what I want to show is it is holomorphic on all of U. For that, what should I do? I want to apply Morera's theorem. Okay. So what does it mean? Take any solid triangle delta contained in U, then I have to prove path integral of F over the boundary T is 0, right? But this is tailor-made. This is the hypothesis of Cauchy-Gursa, right? Therefore, this is 0. Therefore, I conclude F is holomorphic on all of U. Yeah, right. Now I can prove the so-called Riemann's theorem. So U open, Z not a point, F again same U2, C continue U, okay, U minus Z naught is holomorphic, okay, and I am assuming limit Z goes to Z naught, okay, and F is bounded on U. Now you see that I am not assuming F is continuous on all of you. Please note that, not assuming F continuous on U. Okay, right. Then I want to say try to understand how this varies from the just what we proved. There we assume F is continuous on all of you, holomorphic except at one point. Here what I am assuming, F is holomorphic except at one point and F is bounded on U. Remember, is that okay? In fact, I don't even need that strong hypothesis. It need not be even bounded on that. Okay, weaker hypothesis will be limit Z going to Z naught of Z minus Z naught into F of Z is 0. That is, this is Z naught. Okay, in a neighborhood of Z naught, it's bounded. That's more than enough. It may not even be bounded on all of U. You will see this is a weaker hypothesis, what I need for the proof. Don't get confused. Okay, this is how or begin to think. As I said, do not worry about exams. Just learn thoroughly, then read your notes, books, etc. You will understand your concepts are much clear, and you since you have understood the proof, okay, recalling the proof if you want to write in exam, it will also be easy, and it also allows you to solve a lot more problems because the concepts are clear, right? So hypothesis therefore is now limit z going to z naught of z minus z naught into f of z is 0, right? Okay, therefore let us define a function g of z to be z minus z naught into f of z, okay, for z not equal to z naught and equal to 0 for z equal to z naught. Remember, f of z naught may not even be defined because what I define f only on u minus z naught, okay. If you want, again you can be very clear, because since f is defined only on u minus z naught, then you want to say what is meant by f is bounded on u, because it's not even defined at z naught, right? So it is bounded on the complement of z naught. But this is a stronger hypothesis. As I said, this hypothesis is good enough for us. This makes sense, right? Limit z going to z naught, I don't have to worry about whether f is defined at z naught or not. This makes sense. Is it clear? Now what do you know about the function g? Notice that the function g is continuous, okay, because f is holomorphic outside, okay, on u minus z naught, okay, and z minus z naught is a polynomial, therefore product of holomorphic function, this is holomorphic outside at z naught. At z naught it is 0 because limit z going to z naught of g of z is 0 by hypothesis, which is g of z naught. Okay, g of z naught is 0 and limit z going to z naught of g of z is, that is the limit z going to z naught of z minus z naught into f of z. By hypothesis this is 0, okay, and by definition g of z naught is 0. Therefore we proved g is continuous on all of you. Yeah, since g is continuous on all of you, therefore g is continuous on u and holomorphic on u minus a singleton point z naught, right? Therefore by the last observation, okay, application 2 implies g is holomorphic on u. Yeah, beautiful, right? So how did we prove? Go back. These are all, as I keep saying, these are all bootstrap argument. Very small things you keep on doing, okay. See, it's like a shoelace. When you tie, you enter the lace here, on the other side you go one step up and pull it in, the other side you go one step up and so on. So it's a kind of zigzag movement. At the same time you keep on improving. So most of the results in basic parts of complex analysis is a lot of bootstrap argument. So the best way is to review the proof again and again. G is holomorphic, okay. I'm not worried about that g. What I'm worried about is f is holomorphic, okay. I know f from u minus z naught is holomorphic on here, right? Therefore I only have to worry about limit g going of f of z minus f of z naught by z minus z naught, okay, whether it exists, right? Okay, now let's go back. Okay. What I know is, since limit g z going to z naught of, that is g of z minus g of z naught by z minus z naught exists, okay. But what is g of z? G of z is f of z into z minus z naught, right? And this is 0 minus 0 by z minus z naught, that is same as limit z going to z naught of f of z. Okay, you follow that? This is this object gz by gz naught by z minus z naught is same as f of z into z minus z naught divided by z minus z naught, which is f of z. Therefore, the limit z going to z naught exists same as saying limit z going to z naught of f of z exists. You follow that? So call it something like alpha. Define f of z naught to be alpha. Then, okay, f from u to c is continuous because it's holomorphic except at z naught, and f of z naught is alpha, and limit z going to z naught of f of z is alpha, right? And f from u minus z naught is holomorphic, right? Therefore, by application 2 f is holomorphic. It's a really subtle proof, subtle and intricate. It's as simple as I explain, but often if I ask you to explain, it will be very difficult. Even for me, I have to think a bit to do that. Okay, this is a typical bootstrap argument. Okay, like tying a shoelace. Is tying this way. Okay, it's like this. You start from here and go here, and then go here, and then go here, and so on. Okay, you can see how the proof is. Let's go back. You go through the proof once again. Okay, the proofs are very simple. Please go through the proof. This entire video, just go through it carefully. You can see the arguments are how subtle. They are very simple. As I explained, you may think it's very easy, but okay, if you try to recall the proof, you will find it difficult. Okay, right? So twice revise, then you will feel more comfortable. I hope you enjoyed this lecture. And this proof of Riemann's theorem which I had given is different from the one I had given in my book. In fact, this was the original proof which I gave, but while writing the proof I forgot and wrote some other proof. So when we deal with Riemann singularities, etc., I will again prove this Riemann's theorem. It's known as Riemann's theorem on removable singularity. Don't worry about that word, okay? At that time I will again give my proof which is found in the book. But this proof is also very nice. It's a little intricate, whereas the other proof which I am going to give is not that intricate, but this is a very beautiful proof. You should learn. Okay, don't worry about remembering such things. Okay, it's a pleasure of eating. Okay, that taste is good. Okay, like that, here that enjoyment. Okay, the understanding, that is what is exciting. I hope you enjoy. We will meet again.